This is the final video for our Calculus 2 course, and it is over section 10.4, which involves polar coordinates and polar graphs. So far, we have seen graphs using either ordered pairs x, y on the coordinate plane or in parametric form. Today, we are going to look at the polar coordinate system. The polar coordinate system, instead of graphing an ordered pair x, y, we will graph the ordered pair r, theta, where r is known as the directed distance and theta is the directed angle. So in this particular section, familiarity of the unit circle will be beneficial. So if you have not used your trig for a while, the unit circle could come back to haunt you a little bit. So basically, when we are coming up with these polar coordinates, r, theta, again, r is the directed distance from the origin or the pole to the specific point. And there are some different examples I'd like to show you down here. Here, we typically have these concentric circles here. And if this here is the point of interest, the ordered pair is going to be 2 comma pi over 3. The reason for that is because the directed distance is 2, so r is 2, and this ordered pair has a theta value of pi over 3, which is given. And hopefully you remember that pi over 3 is in quadrant 1. Now let's say we are interested in this ordered pair. Well, the directed distance is 3. And this angle is given to us as negative pi over 6. So we're giving the negative value. Remember, if we're given a negative angle, we're heading in this direction here. So this ordered pair is given to us. Now, suppose I have this ordered pair, which might look similar to the previous example. Instead, this angle measure is given to us as 11 pi over 6. And hopefully you remember that 11 pi over 6 is equivalent to negative pi over 6 from your trig class. So this is the same ordered pair, but it's written a little differently. This should be positive, sorry, typo. So these two things are equivalent, but they have different angle measures. That's one thing that kind of stinks about polar coordinates. In this case here, rectangular coordinates, they are unique. You know, there is one ordered pair for each point. However, with polar coordinates, that's not the case. So there are different ways in which you can represent them. So I kind of illustrated that in the previous slide here for parts B and C. So you can have the same directed distance, but your ordered pair could be, your angle could be different. So if you have this ordered pair here, remember that if you add 2 pi to it, you'll get the same thing, and that's what's illustrated here. Similarly, the directed distance can be represented a little differently as well. Take the following, for example. Let's say we are interested in this point here, where, let's call this P. Okay, well, I can also take the opposite of P, which would be here. This is negative P, so the directed distance is in the opposite direction. But what I can do is take this negative P, and then if I add pi to it, then I'll get back to this angle. and that's what's illustrated here. Okay, so it's kind of summed up here. The ordered pair r theta can be written in a few different ways. And, you know, really there are an infinite number of ways you can represent these polar coordinates. So coming up with a few should be okay for you. Now we'll have to make some conversions just like we did in the previous sections. So let's kind of analyze this a little bit. What we've done is we've placed this on a coordinate plane, this r theta, so we can see what's going on. And a couple things you want to understand here is that we have a right triangle, so we can apply not only SOHCAHTOA, but the Pythagorean theorem. So we come up with some pretty important things by applying those rules. This here is one of them. R squared is equal to x squared plus y squared. And then also by applying SOHCAHTOA, we get each of these things. So we're going to be able to make conversions by comparing values for x and y and coming up with theta or r. Okay, so we're going to use these things here. Additionally, the polar coordinates r theta are related to rectangular coordinates xy by these formulas here. If I want to go from polar to rectangular, these formulas are helpful. On the other hand, if I want to go from rectangular to polar, these formulas are helpful. In this class, you really don't have to memorize this if you've kind of picked up on how this course has been designed. So let's go ahead and just jump into a bunch of examples so we can see what's going on here. In this example, we're given the polar coordinate -2, 11 pi over 6. What we want to do is we want to plot this point and then find the corresponding rectangular coordinates, which are x and y for the point. So we are given r and theta. So if I want to sketch a picture of this, remember we have these concentric circles. I know r is 2, and in fact it's a -2, which is going to be important. But we also know what theta is. Theta is 11 pi over 6, and I hope you remember that 11 pi over 6 is in the fourth quadrant because it's not quite 12 pi over 6, which reduces to 2 pi. So if you're taking one revolution of the unit circle, you're going to stop before you reach 2 pi. So this here is 11 pi over 6. Now, this ordered pair here would be 2 11 pi over 6. But our directed distance is a -2, so we are just going to reflect that. So this here, the green one, this is the coordinate -2, 11 pi over 6. Okay, so now that we have it graphed, now we need to find the corresponding rectangular coordinates. And we're going to use the information from the previous slide to find this. On the previous slide, you were told that x is equivalent to r cosine of theta. Okay, well, if that's the case, we know r is given to us as -2. And we want cosine of theta, and we know that theta is 11 pi over 6. Now this is where the unit circle comes into play, so let's dig deep. Now, 11 pi over 6, that means that my reference angle is pi over 6. Pi over 6 has the corresponding ordered pair, √3 over 2, 1/2. So remember, the first value is cosine, and the second value is sine. So I also want you to remember that 11 pi over 6, in our case, 11 pi over 6 is in the fourth quadrant, and in the fourth quadrant, the y value is negative. Okay, so that means this is really negative. Now, if you don't have any idea what I just talked about, you absolutely are going to have to review your unit circle, because I'm not really going to spend a lot of time reviewing that. So this becomes -2 times cosine of 11 pi over 6 then is √3 over 2. The 2's will cancel, so -√3 is the value that we get for x. Now let's find y in a similar fashion. From the previous slide, we found that y is equal to r sine of theta. So again, r is given to us as -2 sine of 11 pi over 6. We have found right here that 11 pi over 6 is -1/2 in that fourth quadrant. So this gives me a value of 1. So we have found that the corresponding rectangular coordinates are, or is, -√3, 1. Now we have the opposite. We are given the rectangular coordinate, so we're given x and y, and we want to find we want to plot this and then find 2 sets of polar coordinates on this interval here. So this is basically 1 revolution of the unit circle. So remember, if we want to find polar coordinates, we want to find r and theta. So from a few slides ago, you should have recognized that tangent of theta is found by taking y over x, and then r rather, is found by taking the square root of x squared plus y squared. Okay, now on that previous slide, it's really r squared is equal to, so I just took the radical of both sides. But I kind of jumped the gun a little bit and I forgot to plot this. So if I were to graph this, x, y, I would find that this here is the ordered pair. I'm just going to draw in a little triangle here, and I know that y is the square root of 3. I apologize. I'm realizing I have a typo here. The original problem, this should be a -√3. And that is why I have this point plotted in the fourth quadrant rather than the first. So I apologize for that. Okay, so now this, and I'm going to leave these positive values. So if this is theta, this is going to be the square root of 3. This is 3, because if we have this triangle, we want to deal with positive values. And that will be r. Now, if I want to find 2 sets of polar coordinates, what I could do is find this one, and then the reflection over here could be helpful. So with a -r, but then add pi to it. Okay, so let's see how that works. Okay, so we have it plotted. Now let's use this information that I've written down from the previous slide. I know that tangent of theta is y over x. So in this case, tangent of theta is equal to the square root of 3 over 3. Okay, so again, the unit circle and some trig comes up. And if that's the case, tangent of theta is equal to root 3 over 3 at multiples of pi over 6. So my reference angle is going to be pi over 6. Well, we are in the fourth quadrant, and I know that in the fourth quadrant, the angle that's a multiple of pi over 6 is 11 pi over 6. So that means that theta is 11 pi over 6. Okay, now we can also find r by applying this formula. If that is the case, then r is equal to the square root of 3 squared plus the square root of 3 squared. This is 9 plus 3, which is the square root of 12. And we can reduce this into a perfect square times a non-perfect square. So this reduces to 2 root 3. Okay, so we have found r. So the easy angle in polar coordinate form is already found for us, or not found for us, but already circled in red. So one of our equations, or not equations, coordinates is 2 root 3 comma 11 pi over 6. Okay, well, another one could be written as negative 2 root 3 comma 5 pi over 6. And the reason for that is this angle here is 5 pi over 6. And if we have a negative angle or a negative direction, that will give me this one. And that's just 2. Again, there are an infinite number of possibilities for these. You could take this. But I guess the thing to be cautious about, which kind of restricts us, is our interval here. So since we have been told that theta has to be between 0 and 2 pi, that kind of restricts us a little bit. Okay? So those are the two answers. Now suppose we have something like this, where it says convert the rectangular equation to polar form and sketch its graph. Well, in the previous example, we were given points, and now an equation is given here, so we kind of need a different approach. So all of the necessary information was given to us already. The hard part is trying to figure out how to use that information. Now, I want to remind you that x is equal to r cosine of theta, and y is equal to r sine of theta. Now, if I have a rectangular equation, remember rectangular equations have x's and y's, whereas polar form has r's and theta. So what I am given has x's and y's, so I know it's rectangular. And I need to change that to something with only r's and thetas rather than x's and y's. So this information is going to be helpful because I'm going to replace x with r and a theta and replace y with an r and a theta. So I'm going to do that right now. So I know that y is equal to r sine of theta, and I'm going to square that. This is equal to 9 times x, but instead of x, I'm going to write r cosine of theta. Okay, well, since this left-hand side is squared, I get r squared sine squared of theta is equal to 9r cosine of theta. Typically in these equations, we want to get r by itself. So In attempt to do that, what I'm going to do is I'm going to divide this by r. Okay, and when I do, these r's cancel. One of these r's cancel. So I have r sine squared of theta is equal to 9 cosine of theta. So I almost have r by itself. In order to get r by itself, now I will divide by sine squared of theta. So r is equal to, in this case here, we can rewrite this as 9 cosine of theta cosecant squared theta. Since r is by itself, we have r, we have theta, we have converted our rectangular equation to polar form by using what I have noted over here. Now, looking at the given rectangular equation, I should be able to recognize that this is a sideways parabola. I know it's a parabola because only one variable is squared, and since the y value is squared, I know it's going to open to the right. Now, sketching it is really not my biggest concern, so do what you can to sketch it. You can put it in your calculator if you want, but you should be able to determine that the graph looks like this. Here's another example, but this example is beginning in polar form, and we want to convert it to rectangular. So polar form again involves r's and thetas. Rectangular involves x's and y's. So again, we're going to have to come up with some way to rewrite this. So note, it's helpful to remember that x is equal to r cosine of theta, where y is equal to r sine of theta. This is often helpful as well. And then in cases like this, it is helpful to use r squared is equal to x squared plus y squared from one of the early slides. These three things are going to help us convert this polar equation into rectangular form. So the first thing I'm going to do, and I'm going to use r squared rather than r, because if I can avoid using that radical, that's going to be helpful. So I need an r squared. So what I'm going to do is I'm just going to multiply both sides by r, because when I do that, the equation is still balanced. So this gives me r squared is equal to 5r cosine of theta. Well, this was super helpful because I know that r squared is x squared plus y squared. And I also know that r cosine of theta is equivalent to x. So this is equal to 5x. Boom. I have my x and my y. That is good enough for a rectangular equation. But we also want to sketch this graph. And looking at this, it's hard to tell what this is going to be a graph of. Well, you may recall from previous lessons that in order to figure this out easily, we may want to put x's on one side, y's on the other, or something along those lines, and maybe complete the square. So that's what I'm going to do in this case. So I'm going to write x squared plus, x squared minus 5x, because I've subtracted that, plus a special little number, plus y squared is equal to 0. And don't forget your special little number over here. Okay, so we're going to complete the square on this. So your special little number ends up being -5 divided by 2. We're going to square that, so 25/4. Special little number, 25/4, 25/4. This here will factor into x minus 5/2, that quantity is squared, plus y squared is equal to 25/4. Okay, well, although this isn't ideal, this is this will be a graph of a circle with the center at 5/2, 0, and the radius is the square root of this, so it will be 5/2. So hopefully you can sketch a little picture of that. Okay, not terrible. Here's a little something else. This one says convert the polar equation to rectangular form. Now this one's slightly different than before because I have cosecant. And so if I take the same approach that I did in the previous example by multiplying both sides by r at first, it's going to get a little hairy. So instead, let's maybe think of another way that we can solve this. Well, I'd like to get rid of this cosecant, and I can do that by dividing both sides by cosecant. And the reason I've chosen to do that is because 1 over cosecant is the same thing as sine. So this becomes r sine of theta is equal to -6. Well, what do we know about r sine of theta? You know, we've done enough of these examples where you should be able to recognize that r sine of theta is equivalent to y. So simply y equals 6 in this case. Boy, was that much easier than by taking a very long approach and multiplying both sides by r. So here is the graph. If only they were all that easy. Now, of course, we will want to find slopes of tangent lines to polar graphs now. We found slopes and tangent lines in parametric form. Now we are going to deal with polar form. So we know that x is r cosine of theta and y is r sine of theta. So we are going to use this and come up with a new formula. All right, well, this new formula, we had this in the previous section. By replacing things, we end up with this formula here. Okay, and this formula has thetas involved, and it's basically established in this next theorem here. So this here is the formula to find the slope in polar form. And there's a little graphical illustration here, which is kind of nice so you can see what's happening. So a couple things you may want to figure out when there are horizontal and vertical tangents. Remember, just like before that we discussed, horizontal tangents occur when this is equal to 0, whereas vertical tangents occur when the denominator is equal to 0. And that's what I'm illustrating on this next slide. So if I have dy d theta is equal to 0, we'll have a horizontal tangent, whereas dx d theta is equal to 0, there will be a vertical tangent. Okay, so nothing crazy there. Let's jump right into some examples. So here in this example, we've been asked to find dy dx and the slopes of the tangent line on the graph in the three indicated points. Okay, so there's kind of a lot going on here, but we are smart people and we can handle this. So the first thing we need to do is find this derivative. So in order to find dy dx, the formula is on the previous slide, and I'll just write it here for us for reference purposes. Now you may notice in this formula that we need to find the derivative of the function. So we'll do that here in a second. Okay, so one thing I want to let you know is that r is equal to f of theta. So this is the function. So in our case, it's 2 plus 3 sine of theta. So if I want to find f prime of theta, which is something that's required in our formula, I want to find the derivative of this. The derivative of this is 3 cosine of theta. Okay, so I have everything I need to find dy dx. So I'm just going to go ahead and plug everything into this formula. So when I plug f of theta in, I'm just going to leave that as 2 plus, I don't know why I keep doing that, 3 sine of theta. I'm going to multiply that by cosine of theta. And I'm going to add that to the derivative, which is 3 cosine of theta times sine of theta from the formula. Then in the denominator, negative f of theta is the same thing I have written above. So negative quantity 2 plus 3 sine of theta times sine of theta plus 3 cosine of theta times cosine of theta. Now some of these have some little tricks. Some don't, but some are easier to find than others. All right, so let's keep going here. All right, we have gone ahead and found dy dx, but now we want to find the slopes of each of these tangent lines shown. So the first one I'm going to do is at 2 comma pi. So let's find the slope here. So what I'm going to do is I'm going to find dy dx evaluated at the ordered pair 2 pi, where 2 is r and pi is theta. Now you can, anywhere you see a theta, you can plug in this pi, but I want you to notice that this is r, right? That is r, and this is negative r. Well, work smarter, not harder. We know that r is 2. So you can replace this whole thing with 2 rather than taking the time to plug pi in for theta. So we end up with 2 times negative 1, because cosine of pi is negative 1, plus 3 times negative 1 times 0, because sine of pi is 0. Again, refer to your unit circle if needed. Here we end up having negative 2 times 0, because sine of pi is 0, plus 3 times negative 1 squared. Simplifying this, I end up getting negative 2, 3. So the slope of this tangent line here is negative 2/3. That should make sense. That line is going in the negative direction, and we found our slope to be negative. Awesome. Let's find the next one. So now I'm going to do this one here. So this is the dark blue. Now we're going to do green. Negative 1, 3 pi over 2. Now you might need to refer to your unit circle. I'm not going to take the time in this video to go into detail. Okay, so here, again, we know this first part is r, so negative 1 times 0 plus 3 times 0 times negative 1 over negative r is, that becomes just a 1, times negative 1, because sine of 3 pi over 2 is negative 1, plus 3 times 0. A lot of zeros here, so this cancels out and the slope is 0. Well, that should make sense. That line, that green line there, is a horizontal line, and those have a slope of 0. The last point is at 3.5 comma pi over 6. So we want to find the derivative at that point, r theta. So plugging this in, so here 3.5 is the same thing as 7/2, and I want to remind you that the ordered pair that corresponds to pi over 6 is √3 over 2 1/2. And the first value is cosine, second value is sine. So that's where these values will be coming from. We have 7/2 times √3 over 2 plus 3 times √3 over 2 times 1/2. All over negative 7/2 times 1/2 plus 3 times √3 over 2 squared. Plug that into your calculator and you'll find this is approximately 8.660. That is a very steep slope, and as you can see here, yeah, that looks about right. Okay, onward. Here we want to find points of horizontal tangency. Okay, well recall, if I want to find horizontal points of horizontal tangency, this means that dy d theta has to equal 0. Well, in this case, dy d theta, oops, I put a theta, this is 0. dy d theta, that is the numerator, which is f of theta cosine of theta plus f prime of theta sine of theta. That has to equal 0. Okay, well, in order to plug things in here, I need to find f prime. So remember that r is the same thing as f of theta. So if I know the given is f of theta, f prime of theta is negative 2 cosecant theta cotangent theta by finding the derivative of this given. Okay, so now plugging it in here, I get the following. 2 cosecant of theta plus 3 times cosine of theta plus the derivative is negative 2 cosecant theta cotangent theta times sine of theta. Okay, now this one, we are not given an ordered pair here. So leaving this first part here, leaving this as r and negative r, that's not going to help me because I don't have an ordered pair. So a different approach is needed. We need to distribute and combine like terms. This cosecant, you might want to think of this as 1 over sine of theta, because when you distribute this, then you have cosine of theta over sine of theta. This gives me 2 cotangent of theta plus 3 cosine of theta. Same type of thing over here. You might want to think of this cosecant as 1 over sine of theta and cotangent as cosine of theta over sine of theta. Well, if you're multiplying by sine of theta, this ends up giving us a negative 2 cotangent of theta. And we know that this needs to equal 0 in order for us to have a horizontal tangency. Well, wow, look at this. These cancel out, and I am left with 3 cosine of theta is equal to 0. If I divide both sides by 3, cosine of theta is equal to 0. Okay, unit circle time. Cosine of theta is equal to 0 here and here, which on our unit circle corresponds to theta values of pi over 2 and 3 pi over 2. So here I have found theta for our points to the polar curve, but now I need to find r. So if theta is pi over 2, I can find r by plugging pi over 2 in here. So to do that, I would have 2 times cosecant of pi over 2 plus 3. Unit circle, 2 times 1, this is 1, plus 3 gives me 5. So when theta is pi over 2, r is 5. This will be one of my coordinates. We're going to do the same thing when theta is 3 pi over 2. Oops, 2. Plug this in here. So 2 cosecant of 3 pi over 2 plus 3. This is 2 times negative 1 plus 3, which is 1. So the 2 points of horizontal tangency is 5 comma pi over 2 and 1 comma 3 pi over 2. Again, we want these listed as r comma theta. And there you have it. Now, this really kind of wraps up the lesson. On this slide here, just read through this. These are referred to tangent lines at the pole. I'd like you to watch the CalcView video, number 77, section 10.4. That will give you another example to look at. And then finally, there are some special polar graphs here, some lamicons and cardioids, and then roses, circles, and lemniscates. It's kind of cool that you can graph these things, but really this is something that is discussed in trig, and we will not go into detail here. I hope you enjoyed this final long video.